Okay, today's video is going to be about variational autoencoders. You might have heard of these before. So the goal is to see a type of autoencoder that can generate reasonable samples that it was not trained on. So recall what an autoencoder looks like. We have this input X, and we run it through this encoder network to some lower dimensional latent space. And then we have a decoder on the other side which reconstructs an approximation of our input. So we'd like to be able to reconstruct samples in our data set, but in fact we'd also like to be able to reconstruct samples that were not even in our data set, any sample. In essence, we would like to sample the distribution P of X, the distribution of inputs. Okay, so we generate samples by choosing elements from some lower dimensional latent space. So I just want to point out this P of X is a distribution. It kind of has two purposes. One is, given an X, it can tell us what the probability or the probability density of that X is. So in that sense, P of X is like a function. Here's some input image X. What's the probability of observing it? The other side of it is always we can sample it. We can say, here's a distribution, please give us a sample. So give us an X, or give us a bunch of X's that generate X's that reflect the underlying distribution P of X. So there are two different things. It can be quite difficult to ask a distribution to generate X's that satisfy the distribution, or that come from that distribution. So one way around this is to generate samples by choosing some latent lower dimensional representation and then generating from those. So we could start with a Z taken from some latent distribution P of Z. So for example, for the MNIST data set, which is what I'm going to be talking about a lot here, the Z could represent the digit class, so is it a 5 or is it a 3? It could also be line thickness, slant, and all sorts of other features that would specify particular samples of the MNIST or some other samples that we haven't written before. So then from that latent representation, we generate those samples. So here's our Z. Whoa, my iPad's being really fussy. And then we can generate X by some function that has parameters theta, and it gives us an X. And so we can think of this function D as generating a distribution, and that's distribution's parameterized by theta. So it'll give us the probability of observing X given some latent representation Z. And then we can compute the P of X as the integral of all these distributions, or all these samples, so in essence we can sample all of Z and then evaluate this integral for a given X, and that way we can get the probability of observing X. So note here, running the random variable Z through D gives a distribution. So running Z through D gives a distribution P of X given Z. So since Z is a distribution, running some random variable through some function gives you another random variable. So in a drawing here, I've got Z here, and I've got some distribution of Z, so this is probability of Z. Then I can run that through D and then get a distribution over X. Probability of X given Z. But even for a fixed, so that's one way in which P of probability of X given Z is a distribution. But in addition to that, going forward, we're going to also say that even for a fixed Z, we assume that P of X given Z is a distribution. Okay, so here's our Z-axis again. We're going to fix a particular Z and then generate a distribution from that. So this will be d of Z parameterized by theta. And here I'm drawing it kind of like a Gaussian function. Okay, so there are two different processes going on here, two different distributions contributing. There's the distribution of Z, and then even for a fixed Z, there's a distribution of X's for that Z. Okay, we'll keep that in mind for now. Okay, so we have a data set of samples X. That's where we're starting from, right? And we're going to try to find some parameter values theta to maximize the likelihood of observing X. Okay, so we basically want to design our decoder. We want to find theta. We want to design our decoder so that when we throw in all our different Z's, we get lots of reconstructed X's that look like our training set. In fact, we'd like to, if we can choose the Z that corresponds to our training data, we'd like to be able to reconstruct our training data. So if we assume that our P of X given Z is Gaussian, with mean equal to the reconstructed, whoops, not like that, and some variance or standard deviation. So just like I drew it up there, we're assuming that our P of X given Z is Gaussian. In that, if that's the case, then the negative log likelihood of X given, of our data set X given Z is going to be, a Gaussian is like something times e to the sort of quadratic function between your mean and your sample. So it'll be 1 over 2 sigma squared times the difference between X and our mu, which is like that. And in fact, it'll be plus a constant. But when you're optimizing, you don't care about those constants. Okay, so we'll come back to this later. But the point is that given some samples, given some images X, if we can find the right Z's, we can reconstruct from those Z's and then compute the negative log likelihood between our reconstruction and our sample, our training sample, and get some measure of reconstruction error from that. So given samples Z, we have a way to learn d of Z theta, that is find the theta values. D of Z theta is our decoder, to maximize the expected value taken over Z, sampled from P of Z, of the probability of X given that Z. Okay? So we've already done that sort of stuff with autoencoders, actually. We've already learned decoders. So that'll be one part of it. Now here's the problem. We don't know how to sample Z. It's just this kind of arbitrary unknown thing. It could be any distribution. In fact, Z, if Z is a 10-dimensional space, we'd have to integrate over or sample all of this 10-dimensional space, which is just infeasible. It's intractable. So let me illustrate why this is a problem. Suppose we train an autoencoder on a data set of simple shapes. So let's suppose my shapes are circles, triangles, and squares. So in the latent space is 2D, and the clusters are well separated. Here I'm showing them trained, so you can see the 3 different clusters in 2D, and I've shown which shape each cluster corresponds to. So now let's say that we choose a sample here, and we reconstruct from it. So what shape might we get from this? I'm going to say, well, it looks like that. What about if we sample over here? I'm going to say the sample looks like this. Those don't look like shapes. So in terms of generating samples, like we've trained our model on this data set, now we're ready to generate samples and we're interested to see what other new samples it can produce for us. We get this garbage. Okay, another example, MNIST. So I trained an autoencoder on MNIST, and then I just generated a bunch of random samples. You can see the random samples here are in black. And so from those, I decode those random samples using my decoding part of my autoencoder. And I get things, some of which look like images or digits, but many of them don't look like digits. Many of them look like just kind of like wispy digit-like sort of things. So that's not what we want. I don't really have a model that generates good-looking digits consistently. So what's happening? Why is our generator so bad? Why is our generative model so bad? The answer is we're choosing improbable Z samples. And where P of Z is approximately 0. So we're choosing parts of our latent space that don't really contribute to the full probability density function for P of X. So I'd like to take a little bit of time to tell a joke. So a wife says to her programmer husband, "Go to the store and buy a loaf of bread, and if they have eggs, buy a dozen." So the husband returns with 12 loaves of bread. Okay, we'd like a way to choose, like to sample only the Z values, only the Zs, that yield reasonable samples with high probability. So now we're placing requirements on the distribution in our latent space, and we ask ourselves, can we do this? And the answer is yes. We have enough flexibility. So let's assume that we choose the distribution of Zs in the latent space, and we're going to call this distribution Q of Z. Then we can evaluate the probability of X as the expected value. This is what we had before. Z was taken from some unknown distribution P of Z before, and where you evaluate Px given Z. So that's basically the sort of sampled equivalent of, I guess that right there. I mean, that's also sampled, but it's the sampled equivalent of this thing here. It's the expected value. Okay, but that can be rewritten in summation notation where I take Z's from my distribution P of X given Z times the probability of Z. That's what the expectation means. But I'd like to change the variable, change the way I sample my Zs. Instead of using P, which is an unknown distribution. I want to sample it from Q, which is my designed distribution. So I'm going to take Z's from some Q. Now, so I don't change the value of the thing in here. I'm going to multiply on the top and bottom by Q of Z, which is the probability of observing Z. And then I can rewrite my expectation, Z sampling from Q of P of X given Z times P of Z over Q of Z. So I just rewrote that expectation, but now I'm sampling from a different, I'm sampling my Z's from a different distribution. And that P of Z over times the P of Z over Q of Z is basically the factor you would add in for importance sampling, which is something from statistics. Okay, now the negative log likelihood of that is what we'll be looking to maximize, right? Maximize or minimize? Maximize. We want to maximize P of X. And so over our data set, we'd want to, or over our samples, we want to maximize the negative log likelihood. So negative log P of X is negative the expectation. I'm just going to write it like this, over Q log P of X given Z. Let me write a little more clearly. There we go. Plus log of P of Z over Q of Z. Okay, now this first term is just the expected value of the negative log likelihood. You can't do much with that. The second term, though, is the KL divergence between Q of Z and P of Z. So maybe you've not heard of KL divergence before, but I'll just quickly write it here lightly. KL divergence between Q and P, I mean, it's pretty much just the definition above there. It's a sum of Q times the log of P over Q over some random variables. P and Q basically measures the difference between distributions. So the more similar the distributions P and Q are to each other, the smaller KL divergence becomes. So it's divergence. It's sort of distance, a distance measure. Now I'm going to call, I've reordered my terms here. I'm just to be consistent with the notes I have that I'm looking off of. I'll call this 2 and I'll call this 1, even though I on the fly decide to switch the order of them. Okay, so let's look at 1 first. So let's choose a latent distribution that's convenient for us. So we don't know what P of Z is, but it seems that we have some flexibility to choose what we want our latent space to look like. So let's choose a latent space representation that's convenient. So we're going to say our P of Z is going to be normal with mean 0 and covariance matrix, identity matrix. So then our aim is to design Q of Z so that it's close to this, what I'll call the standard normal distribution. So in other words, we want to minimize over these different Q's the KL divergence between Q of Z and normal 0, 1, or sorry, 0i. So how do we design our latent representations to achieve this? So let me remind you, the problem is we don't know how to sample Z. right? We want to generate new MNIST digits or new samples. But in order to do that, we have to know something about our latent distribution. So we've made some progress. We said, let's suppose that our latent distribution is a standard normal distribution. Okay, so how do we, but we need to, now we still need to figure out how to create our latent representation of our digits. We need to know which latent, how to represent our digits in our latent space, I guess. Okay, so how do we design our latent representation so that it's a standard normal distribution? So the answer is we design our encoder. We still have the flexibility to design our encoder, and we ask its outputs to be distributed normally. Okay, so here's our encoder X, sorry, our input X, and we have an encoder, and it's going to output now a mu and a sigma. So we'll talk about the standard normal in a minute. Right now, we want it to output some distribution, some normal distribution, and for the time being, we're going to say, well, its distribution is going to be defined by two different things that it outputs. It's going to output a mean, mu, and a covariance, sigma. So this defines a distribution, normal, mu, sigma. Okay, so bear with me. In terms of MNIST, we've got some input image. We're going to encode it into some latent space. I'll just draw the latent space as 2D. Encoder, and it's going to land at some mu here, and it's going to have some covariance or some standard deviation, sigma. So this is the latent space. Okay, so our encoder is going to output a mu and a sigma. Now, I already told you, though, we want our latent space to be to have a standard normal distribution. So we're going to pressure our encoder to try to push mu to be 0 and push sigma to be 1, or identity. So we're going to keep pushing the encoder towards mu, giving us a mu equals 0 and a sigma equals I, or 1. Okay, now, since it's giving us this distribution normal mu sigma, we can calculate the distance or the difference between that normal distribution and the standard normal distribution. And the nice thing about the normal distributions is there's a closed form expression for the KL divergence between two normal distributions. And so I'll write down the version of it where one of the normals mean mu and standard deviation sigma, and the other one is the standard normal. But there's a closed form solution for two arbitrary Gaussian or normal distributions. This is a simplified version because one of the normal distributions is a standard normal. Okay, so that's the formula. You can work it out yourself. I worked it out myself. I'm trying to remember how hard or easy it was. Maybe I'll put it in the exercises. Okay, so we want to minimize this. This is one of the things that's going to, minimizing this is going to be pushing our latent representation, or the distribution in our latent space, to a standard normal distribution. And that'll help us because we'll know where we can go to sample to generate, we'll know which Zs we should focus on to generate good-looking reconstructed samples. Okay, so we want to minimize that KL divergence. We want to push our latent the distribution in our latent space towards the standard normal distribution, but it's not that simple. I mean, that would be pretty easy to do, but we still want our latent space representation to be able to generate different digits. Okay, so there are other forces at play. So we have other things to think about. So now we get to term 2, the other term that was up here. This one here. Now this is basically the reconstruction loss. The other term in the objective, which is the expected value over Q of log x given z, is our reconstruction loss, which we can write. So we're going to write that as the expected value of log p x given x hat. Now that's because I guess I haven't talked about a decoder yet. That's because we're going to create did we talk about a decoder? Yes, we already have a decoder. So given our latent representation and some parameter values, we know how to decode that. So I've replaced this z here with an x here just to make it look more like a loss function. But we can do that. That kind of makes sense because we're feeding our x through our network and getting this x hat out of the network using the encoder and the decoder that we've been playing with. So our z comes from mu of x theta, right? That was the encoder I talked about up above, times epsilon sigma x theta, where epsilon is taken from a normal distribution, a standard normal distribution. I'll talk about that in a second. And our x hat is the decoder applied to that z, and it also has, I'm just writing theta for all the parameters in our encoders and decoders. And now this is a deterministic decoder. But remember, we had a deterministic decoder, but that our distribution of our outputs took that deterministic decoder, or took that sort of the output of the decoder, and then put that in a Gaussian, or maybe it's in a Bernoulli or whatever. Okay, so we have these two pieces of our objective. We have our loss, our reconstruction loss here, and we have our KL divergence between our latent space representation and the standard normal. So let me give you a bit of intuition about this. So think of a cloud of matter floating in space, but it's collapsing in on itself by its own gravity, and eventually is going to form a star. Okay, so in the first phase, we have a bunch of matter coalescing. I had to copy because I just don't know how to spell coalesce on my own. So there's a bunch of like atoms out in space, or maybe even molecules out in space, and they're starting to fall in towards each other, towards their center of mass. So all points are pulled in because of gravity. So as time progresses, they start to take up less volume and bump into each other, and that causes heat. So they're falling in towards each other, we're getting an increased density, a lot more of them pressed in a small area. And I'll write it like this. So they're starting to interact with each other, these different atoms. So interactions between these points starts to be a factor. And I mean, it starts to be a factor in how they're distributed. They can't collapse down to a single point in space because they push each other away as they're collapsing in. Finally, as even more time goes on, they balance. So you'd end up with all the points sort of in a region here, and if it's a star, it's giving off light, giving off light. So at this point, the repulsion between the points is equal to the inward pull of gravity. Or whatever's pulling it in. So the metaphor I'm drawing here, of course, is we're just like in our variational autoencoder, this is our latent space representation. We're asking them all to kind of pull in towards the origin to form a standard normal distribution, but there's more at play because we have to be able to reconstruct our samples, reconstruct our MNIST digits, for example, from this latent space representation. So we do need to keep some structure in there. So that's kind of like the tension between the points. They can't all collapse down into just on top of each other into a standard normal. They still have to keep some structure. So there's this balancing act between the reconstruction loss and the KL divergence loss. So here's the process for variational autoencoders. You start out with some encoder and decoder parameterized by theta. They're neural networks. So let me just write that. Start with theta, so network parameters. So you encode x by computing mu of x theta and sigma of x theta. So this is the encoding into the latent space. Now we sample. I said I would. Yes, I will talk more about that epsilon. We sample the latent space. So this gives us a distribution in latent space. We need to sample that latent space. So Z is equal to mu plus epsilon times sigma, where epsilon is taken from a standard normal distribution. Okay, so I'll explain later that it's important that epsilon is the random variable here. Mu and sigma are deterministic. Okay, then we calculate the KL divergence loss. So we know our mu, we know our sigma, and so it's equal to 1/2 sigma squared plus mu squared minus ln sigma squared minus 1. So that loss is going to be used in our AutoGrad stuff. This is going to be part of that's going to be one thing we're going to use in our optimization. So when we compute that KL loss, we're going to add it to our objective function and take the gradient. Okay, so now we have to decode. We have our Z in our latent space. Now we decode x hat using another neural network. So x hat was, I could call it f of x theta if you want. That goes from input all the way to the output, but it's actually the decoder applied to the Z, which is mu x theta. I'm just drawing it this way to sort of show that you can go from end to end. Oops. Okay, so we decode our, reconstruct our approximate output. Then finally we calculate the reconstruction loss, L, the difference between x and x hat. So for example, if our output distribution is assumed to be Gaussian, the negative log likelihood of that gives us mean squared error. Or, if you assume your output distribution is Bernoulli, then it would be something more like this, x log x hat for Bernoulli p of x given x hat. Maybe the x and x hat should be switched, I'm not sure. Okay. So then both terms of our objective function are differentiable with respect to our network parameters theta. Differentiable with respect to theta. So our objective function is the expected value over all of our input data, our data set, L of x, x hat, where x hat is our output from our encoder decoder, plus beta, which I'll talk about in a second, times sigma squared plus mu squared minus ln sigma squared minus 1. Now, this x hat, oops, that's not what I wanted. This x hat here, and this sigma, mu, that sigma, those are all dependent on our network parameter. They're all computed using neural networks. Okay, so we can do gradient descent on theta. We can ask to minimize that objective function with respect to changes in theta, our network parameters, the weights and biases in the encoder and the decoder. This beta is a way of adjusting the relative weight between the KL divergence term, how much we're going to insist that the latent distribution be standard normal, versus how much we care about generating the samples in our training set, the loss, the reconstruction loss. Okay, so what does this network look like? So we started with an X here, and you can sort of see that there's this encoder here, which depends on theta. Now that encoder also, I'm showing some sort of layer in between, but ultimately it's going to spit out, I knew that happened, okay. It's going to spit out a mu and a sigma. Two separate latent space things, I guess. So there's theta in here as well. Now what we do with these is we construct a normal distribution from them. So we're going to add together mu, so the mean, plus some disturbance, some random noise that is scaled by sigma. So the way we do this is we choose an epsilon, I've mentioned this a few times, an epsilon that's taken from a standard normal, and we multiply that by our sigma. This is going to give us a normal distribution with standard deviation sigma, and then we add that to our mu. That gives us a normal distribution with mean mu and standard deviation sigma. And that goes into our decoder. And finally, we get our output x hat. Now, the important thing here is that there's stochasticity here. You can't take the gradient, you can't push a gradient through a stochastic variable. You can handle the gradient you can handle deterministic gradients if there's stochastic inputs, because you're not having to push the gradient through an input. So in this context, this epsilon, standard normal epsilon, is an input to the network, but everything else going all the way from this x on the right to the x on the left here is a deterministic neural network. So therefore you can push the gradient all the way through it. This is called a reparameterization trick, where as long as you can use the standard normal, or you don't have to change the distribution of this input epsilon, you can keep the rest of the network deterministic and push the gradient down through it. Okay, so let's see how this works. Because the variational autoencoder seeks a distribution in the latent space that's close to standard normal, there are fewer holes, and we have a better idea of where in the latent space we should be sampling in order to generate reasonable looking images. So again, here's a different latent space, and again the points are chosen randomly. But randomly from standard normal. You can see the origin is about here, right? 0, 0. So there was those black dots, when they're decoded, produce these digits. And I think you can convince, they're not all perfect, but I think you can hopefully convince yourself that they look better, they look more consistently like digits than the ones earlier in the lecture. These ones here. So these, a few of them look like digits, but many of them do not look like digits, as opposed to these where most of them look like digits. In fact, I'd claim that all of them look digit-like, even though some of them are a little bit ambiguous. This one, the bottom left here, looks like it's kind of a cross between a 2 and a 0. I mean, interestingly, you could probably, if you knew which, let's see, 2 and 0. I color-coded these according to like a rainbow spectrum. So black is 0, red I think is 1, yellow or orange is 2. So anyway, I think blue is, no, black, so it's between black and yellow. So maybe this is the one here. It's kind of between yellow and black. No, I'm not sure which sample it is. But anyway, each of the interpolation is much more intuitive in a variational autoencoder latent space. There's more of a continuous transition from one digit to another, instead of having one digit cluster here, one digit cluster here, and this chasm in between that generates nonsensical samples. Now, just to finally put it in the context of this shape example that I gave before. So you can see now those clusters are all pushed together instead of being separated out far from each other. And if I were to take samples here, let's say I take a sample from here, I'd expect that sample to look like a kind of a compromise between the circle and the square. So maybe it'd be kind of like a rounded square. And one over here would be kind of a triangular square, kind of a, oh no, maybe it'd be like this. And then over here, I'd have something between a circle and a triangle. So kind of a rounded triangle. Again, because there are fewer gaps in the latent space. So variational autoencoders, in summary, are basically trying to fill in the gap and produce a much more predictable latent space representation, which approximates the standard normal distribution. So when it comes time to generate samples from our latent representation, you can choose things from the standard normal distribution and expect to get digits that look pretty reasonable, or output samples that look pretty reasonable. And it's a balancing act between forcing the latent space representation to be standard normal and the quality of your reconstructions. You do have to trade them off. You can expect that the reconstructions from this autoencoder will be not as high quality as an autoencoder that doesn't have any constraints on the latent space representation. But it does have the added bonus that the latent space representation is much smoother and tends to have no or fewer holes in it where the latent representations don't correspond to any digits.